and base. Base to acid is 2 to 1. Acid and base is 1:2 ratio. Okay, so that 1.5 is the molar ratio. So you figure out the number of moles of the acid, you can calculate the molarity of the acid there in 0.0562. Okay, so this is one type of calculation that involves the titration there. Given the volume of the liquids that we have, the solution that we use, given the concentration of one of the substance, we can figure out the concentration of the other based on the balanced chemical reaction equation, based on the definition of molarity. Okay, now more chemist try problem. So if you have phosphoric acid, H3PO4, now if you 35.6 milliliter of 0.225 moles per liter sodium hydroxide is required to completely react with 18.9 milliliter phosphoric acid solution. What is the molarity? A lot of information in there. Okay? I actually have to take 2 breaths before I finish the sentence there. I'm reading the question there. So what we have here is that given a balanced chemical reaction equation, we know the molarity of sodium hydroxide. We know the volume of the sodium hydroxide. Now, if you know the molarity, if you know the volume, you can figure out the number of moles of sodium hydroxide. If you can figure out the number of moles of sodium hydroxide, every 3 moles of sodium hydroxide will react with 1 mole of the acid, phosphoric acid. So 1/3 of the number of moles of sodium hydroxide is the number of moles of the acid there. Okay, so that's how we do it. Once we know the number of moles there, we have the volume, we can calculate the molarity. So step by step, we find the number of moles of sodium hydroxide based on the information given here. Molarity times volume, that's the number of moles of the sodium hydroxide. And then we determine the number of moles of phosphoric acid times 1/3. This 1/3 comes from the molar ratio here. And the way that you set up, again, you want to make sure you put in the quantities there. 1 mole of the acid will react with 3 moles of sodium hydroxide. If you have the sodium hydroxide there, if you have the number of moles of sodium hydroxide there, sodium hydroxide cancels out. Very much similar to the previous question. The previous question, the molar ratio is 1 to 2, so it's 1/2. Here, it's 1 to 3, so it's 1/3. Okay, and once you get the number of moles there, divided by the volume, you get the molarity. So again, the step-by-step calculation is outlined in here. I want you to, after class there, I want you to go through these calculations, make sure that you know how to set up the equation and how to do the calculation. It's very, very important. There are plenty of homework questions in chapter 4. You need to know how to set up the equation, how to do calculation. Now, when we introduce that molarity, so we open a can of worms there. There's a lot of other types of calculation, not just about the titration there. We can actually determine, here's another question there, we can ask you to determine the percent composition. That's, in essence, is the key for the Center for Chemical Analysis. We are always trying to figure out how much of a particular component is present in a given mixture there, and this is an example. If you have oxalic acid, okay, it's an acid, you have 4.554 gram of that acid mixed with other things that's not reacting with sodium hydroxide. And you prepare oxalic acid by dissolving the sample in water, and you come up with a solution, right? You do the titration. Based on the number of moles of sodium hydroxide that you use, we can actually determine in that 4.554 gram of the sample that you have to begin with, how many grams of it is actually oxalic acid. From there, we can ask you to calculate the percent composition. Okay. So this is the balanced chemical reaction equation between the acid and the base. Every mole of acid will take 2 moles of the base there. So when we ask you to solve for the calculate the percent composition of the oxalic acid in the mixture there, we got to figure out the grams of oxalic acid. We can determine the moles. Given the formula, we can determine the grams there. So step-by-step solution for this question there. First, we want to determine the number of moles of sodium hydroxide. You were given the volume, you were given the molarity. 0.550 moles per liter. We're using 29.58 milliliter converted into liter here. So this will give you the number of moles of sodium hydroxide. Once you know the number of moles of sodium hydroxide, the moles of OA, oxalic acid, would be 1/2 of that because of the mole ratio. Every mole of acid takes 2 moles of the base. Okay, so this is your conversion factor based on the balanced chemical reaction equation. It's not a random number of 1/3 or 1/4 or 1/4 or 1/2. It's based on the balanced chemical reaction equation. So you figure out the moles of the acid, and you can also, you can also figure out the grams of oxalic acid. You know the moles, you know the formula, H2C2O4. You add everything together, and you get grams, 90 grams per mole of oxalic acid, and you get the grams. Once you get the grams there, now this 90, again, comes from the formula, molar mass here. 2 hydrogen, 2 carbon, 4 oxygen. You find the atomic mass and add them together, you get 90 grams per mole. And then you can calculate the percentage. In that 4.554 gram of oxalic acid mixed with other things, there is only 0.73 to 1 gram of oxalic acid. So the percentage would be somewhere around 16.1%. So this is one thing that we can, another thing that we can do in terms of chemical analysis. We can determine the percent composition of a chemical based on the balanced chemical reaction equation. So as we do many different types of chemical analysis in chemistry labs there, these are the things, once we know how to measure concentration, these are the things that we will be able to do. And no, chemists try, we're never tired of trying. There's another example there. Determining the molar mass of a compound. Say if you have a weak acid, the molar mass is unknown. You can measure out certain amount of acid, dissolve it in water, conduct a titration there. Now, you can't have a situation where you have absolutely no knowledge of that compound whatsoever. In this case, we say, well, A represents the unknown part of the acid. We have 3 hydrogens in this acid there. So when hydrogen react, when the hydrogen in the acid react with the sodium hydroxide there, and that's where the water is formed in the salt. Okay. We don't know what A is. In this case, we want you to figure out what is the molar mass of the acid. Well, if we don't know what A is, how can we figure out the molar mass? We need the information for all of the atoms involved in there so we can add atomic mass together. Well, that's the way when you know the formula. And this is the case when you don't know the formula, you can still figure out the molar mass. There are different ways. Tomorrow in the lab, we're going to ask you to determine the molar mass of a volatile liquid. Not giving you the formula, but going through an experiment, the procedures of the experiment there, you will be able to determine the formula. Okay, so this is an example there. 48.15 milliliter of 0.625 moles per liter sodium hydroxide is required for the titration. This is the balanced chemical reaction equation. A, what is it? What we don't know. We don't have to know. We will be able to figure out the molar mass of this compound when we finish the calculation. Here's the solution there. Everything show up on one slide there. So you have the molarity of the sodium hydroxide, you have the volume there. These two numbers multiplied by one another and gives you the number of moles of sodium hydroxide. And then molar ratio between the acid H3A to the sodium hydroxide is 1/3. Each mole of base requires